The experience of the eclipse is that you're conscious of being, in some ways, insignificant. What I experienced here was roughly 93 or 94% total. It's a rare event. What would have our ancestors thought about this before there was an understanding of how the solar system works? Well, the aim of my research is to understand how life changed the planet and how the planet changed life over immense periods of geological time. The sun's luminosity has increased since the solar system formed, and this has been a problem that's been dealt through models. The astronomers understand how stars evolve through time, and at the beginning of the solar system the sun was significantly dimmer than today. We have evidence of ice covering the surface of the planet roughly 2.4 billion years ago extensively, and then again between say 750 and 630 million years ago. So there have been episodes when the planet has been encased in ice. We know from the recent research into extrasolar planets that the solar system that we live in is far from unique. My understanding is that many stars have planets circling them. We don't know of the existence of a lot of Earth-sized planets or planets in what is known as the habitable zone, but there certainly are. So I expect that there's life beyond Earth, but I don't know that there's any compelling evidence of another form of life within our solar system. The most likely place, of course, that people are looking is Mars, and there have been several robotic missions to the surface of Mars, but in my estimation, none of the data that's come back has compelling signals of another life form on Mars. I think it's even more remote that life will be found on icy moons of Saturn or Jupiter. People are looking, all good fortune to their hunt, but I think that the life on Earth, life as we know it anyway, is largely powered by the sun, and I think proximity to the sun is crucial for the development of advanced organisms, even advanced microbes. I think microbes that exist solely on by eating rocks, I think that's a very difficult way to earn a living. And I think it's proximity to the sun that enables the planet to have liquid water all over it, everywhere. I think that's what is making Earth habitable, and I don't see conditions anywhere near as adventitious for life beyond the Earth. Since life first arose on the planet, perhaps 4 billion years ago, until the present time, organisms have carried out chemical reactions that have dramatically changed the surface of the Earth and the way the Earth is today. And the most dramatic of those changes is when organisms such as cyanobacteria learned how to harvest light from the sun, at the same time using water as a reductant. They learned to do oxygenic photosynthesis. That's photosynthesis that releases oxygen into the atmosphere, and gradually accumulated to what we have at the present day with 21% oxygen in the atmosphere and fully ventilated or mostly ventilated oceans. And that oxygen is what allowed life to become more complex, because life uses that oxygen in ways that produces a lot more energy than you can gain in the absence of oxygen. Over the years, I got more focused on natural products that are preserved in sedimentary rocks, that is, ancient natural products or compounds produced in the main, by microbes in the environment. And the structures of those molecules tell us something about ancient life that you don't learn from the study of conventional fossils like this tree. We look at this, we can see, if you look at the top, you can see rings. You can see it's very obviously a fossilized piece of tree trunk. This particular sample here is a coral, and it's a coral that was collected from 30 years ago, but it comes from a modern reef, and you go to coral reefs around the tropics and you'll find pieces of rock like this, and it's very obvious that it's a coral, but it's not a fossil. Well, I suppose it's on its way to being a fossil, but it's unaltered, it's not changed. The organisms that created it have disappeared from it, but the skeleton is very clearly a coral. This one is a couple of 100 million years old, and it's definitely fossilized because the structure of the tree has been preserved in silica. So it is a fossil, but it's undoubtedly a tree. And if you take slices and look under the microscope, you'll see the structure of timber very clearly preserved in that. So that's a really, really well preserved fossil. This is the next one. This one's about 400 million years old, and it's a trilobite. And you know, paleontologists have been studying these things for years and years and years, and they know it's like a crustacean. But this thing, this sort of organism is now extinct. They went extinct about 250 million years ago. But it's got very clear resemblances to crustacea. So that is a really well preserved fossil of an animal, and its place in the history of animal life is not in any doubt. Now we get to pieces of rock that are about 580 million years old, and they're bits of red sandstone. They come from the Ediacara Hills of South Australia. The objects in them are very poorly preserved because they've been exposed to water, the atmosphere, for years and years and years. It was only, I guess, in the 50s that people realised that these things actually have fossils in them, but they're just shapes and imprints in the rock. So they're effectively like footprints that the organism was there, was covered in sand, the organism decomposed, but the sand where the organism was lying is still preserved. But people are uncertain about the affinities of this, or whether they know where this sits in the tree of life. There's a lot more dispute about where these forms fit in the tree of life, partly because they're strange, but also partly because the preservation is much poorer. So we're going in a sequence from something that's not a fossil, very well preserved, and the degree of preservation has declined. So there's more argument about what the heck is this? What does this mean? This one is well preserved in a sense, but it's not an animal anymore. This is from a world when the Earth was entirely microbial. There were no multicellular animals or plants, as far as we know, roughly 800 million years ago, when this particular rock formed. As I said before, it was formed probably by cyanobacteria or slimy organisms growing on a surface and gradually accumulating sediment and building up these particular forms known as stromatolites. But because there are modern equivalents of this, there are modern stromatolites living in different parts of the world, particularly in Australia, in Shark Bay. There's no longer any scientific doubt that this represents complex microbial community that was once harvesting sunlight. It was living in a shallow coastal environment, making its living from harvesting sunlight. And this rock, This rock is much older. This is 3.5 billion years old, and it comes from a place in the Pilbara region of Western Australia. And scientists many years ago were looking at rocks like this, and the reason they chose to look at rocks like this is because it's mostly silica. And silica is known as a good preservative, like it preserves the structure of the tree. And people are looking in these rocks for preserved microbes. And there are objects in this rock that look like preserved microbes. And it was thought for many years, some people still think it's true, that those microbes represent ancient light harvesting microbes like cyanobacteria. But the preservation here is awful. So to get a convincing, to use this rock like this as convincing evidence of the evolutionary development of life 3.5 billion years ago is very, very difficult, very speculative. When you have macroscopic evidence of life, it's very obvious, generally very obvious, but as you go back in time, it becomes more and more ephemeral, easily disputed, easily argued against. Personally, I think chemistry is one of our best means of telling us about the antiquity of life, because life conducts chemical reactions that has precursors and products, and they have different isotopic ratios, different chemical features that really can only be imparted by biochemistry. What I'm trying to show you is a rock that I'm very interested in, and a lot of my colleagues are, known as banded iron formation. And I see this as a chemical fossil, not a fossil of an organism, but fossil of rust. It was the sediment was deposited or formed in an ocean basin, and it's hypothesized to have been formed when the deep ocean contained dissolved iron that came out of subsea volcanoes, and that dissolved iron reacted with oxygen in the surface of the ocean, the oxygen being produced by oxygenic photosynthesis by cyanobacteria, and the meeting of the oxygen and the reduced iron created this rust. This rock is dated at pretty close to 2.5 billion years ago, and if that theory of the way these things formed is correct, it means that oxygenic photosynthesis had already appeared on Earth at the time this rock was deposited. So this is evidence for the antiquity of light harvesting photosynthesis that simultaneously produced oxygen. And as I said earlier, the history of oxygenic photosynthesis is a fascinating thing. We wouldn't be here on the planet without that oxygen. And understanding how it arose and how the planet became oxygenated is a compelling, I think, scientific topic that should interest everybody, because the oxygen we breathe had to come about somehow, and understanding that I find as a very intriguing scientific problem. It was a great honour to be selected as a participating science on the Curiosity mission. The launch of the probe, this exciting moment. I remember very vividly that moment in August the 6th, 2012, when Curiosity landed on Mars. I was at the Jet Propulsion Laboratory in Pasadena in a room with several hundred scientists and engineers, and the first sign that the rover had landed safely was an image that flashed up on the screen showing the part of the rover wheel and a shadow. At that point we knew that the mission had successfully landed and that we would have several years of exploring Mars ahead of us. I stayed in Pasadena for roughly 5 months We initially started working on Mars time, which meant that the day was rolling along. The time frame was changing by a few minutes each day. So we started out, it was late at night that it landed, and for the first few weeks it was to look at data coming down from the rover. It was a fantastic collaboration that, it's big science when you get so many people working together to achieve such an outcome. I think the scientific outcome is a demonstration that Mars was likely habitable 3.5 billion years ago. Certainly life could have existed, may have existed, but nothing from the Curiosity mission so far provides unambiguous evidence of life early in Mars history. But like the Earth, Mars also has changed over time, and it's much smaller. It lost its water, and its water has gone into space, and it's left a very oxidizing environment, the red planet. It's red because of oxidized iron on the surface, and without that water, it would be very, very difficult for life to persist to the present day. We've been studying life on Earth for, hundreds and hundreds of years in a scientific manner, and with the advent of new instrumentation, computers, better and better tools, we are able to refine the way we do our work. It's a process, and I'm sure the people that work on this when I'm long gone will be able to have even deeper insights into how life has changed the planet.